Essential hand tools for an apprentice electrician's tool belt should include a tape measure, linesman's pliers, needle nose pliers, diagonal cutters, stripper slush cutter, combination screwdriver, Phillips screwdriver, hammer, utility knife, torpedo level, flashlight, chalk line, electrical tape, and wire nuts. Klein Tools is a recommended brand for many of these items. A 25-foot or 30-foot tape measure is ideal for general measurements. Look for 8-inch or 10-inch linesman's pliers with insulated handles. 6-inch or 8-inch needle nose pliers are suitable for fine work. Diagonal cutters in 6-inch or 8-inch sizes are great for cutting wires. A stripper slash cutter, also in 6-inch or 8-inch size, is needed for removing wire insulation and cutting wires. A combination screwdriver with 1/4-inch and 5/16-inch bits is good for general use. You'll also need a Phillips screwdriver with #1 and #2 bits for driving Phillips screws. A 16-ounce ball peen hammer is useful for driving nails and staples. A utility knife is essential for cutting various materials. A 9-inch or 12-inch torpedo level is necessary for leveling conduit and other components. A flashlight is needed for illuminating dark workspaces. A chalk line is used for marking straight lines. Electrical tape is important for insulating and securing wires, and wire nuts are used for connecting wires. Other recommended brands include Milwaukee, DeWalt, Channelik, Greenlee, and Fluke. When selecting tools, choose those that are durable, insulated for safety, and comfortable to use. It's best to start with a basic tool set and gradually add specialized tools as needed. Remember to keep your tools organized and clean for efficiency and safety. Consider purchasing a tool belt or pouch to carry your tools conveniently. Be prepared to invest in quality tools that will last for years. For more detailed tool specifics, firstly, consider a magnetic tipped screwdriver set, as this can be invaluable for holding screws in place, especially when working in tight spots or overhead. Secondly, a voltage tester, specifically a non-contact voltage tester, is crucial for safety, allowing you to check if a wire is live without making direct contact. Thirdly, consider getting a set of nut drivers. These are helpful for tightening nuts and bolts, providing more torque and control than a standard wrench in certain situations. Fourthly, a wire bending tool can make bending wires easier and more precise, especially when working in panels or junction boxes. Fifthly, a set of insulated screwdrivers is vital for working safely with electrical components. These screwdrivers are designed to protect you from electric shock. Sixthly, a good quality pair of work gloves will protect your hands from cuts, scrapes, and burns. Seventhly, consider a headlamp, which is useful for hands-free illumination in dark or confined spaces. Eighthly, a set of Allen wrenches or hex keys will be needed for working with certain types of electrical equipment. Ninthly, a small broom and dustpan can be useful for keeping your workspace clean and free of debris. Tenthly, consider a circuit finder, also known as a circuit tracer, which can help you identify the correct breaker for a particular circuit. It is important to address the National Electrical Code, or NEC, requirements for personal protective equipment and tool safety. Article 110.3. B of the NEC covers the requirements for equipment suitability. This section emphasizes that all equipment used in electrical installations must be approved and suitable for the specific purpose, installation, and environment. This includes hand tools, power tools, and testing equipment. Equipment should be evaluated based on factors such as voltage, current, insulation, and environmental conditions. Article 110.9 addresses interrupting rating. Equipment intended to interrupt current at fault levels must have an interrupting rating sufficient for the nominal circuit voltage and the current that is available at the line terminals of the equipment. This is particularly relevant for circuit breakers and fuses. Article 110.12 covers mechanical execution of work, which requires that electrical work be installed in a neat and workmanlike manner. This includes properly supporting and securing cables, neatly arranging conductors in enclosures, and ensuring that all connections are made correctly and tightly. Poor workmanship can lead to overheating, arcing, and other hazards. Article 110.13 discusses mounting and cooling of equipment. Electrical equipment must be mounted securely and in a manner that allows for adequate cooling. Overheating can damage equipment and create a fire hazard. Proper ventilation and clearance around the equipment are essential. Article 110.14 covers electrical connections, emphasizing that connections must be made with suitable connectors and terminals. The connections must be tight and provide good electrical contact. Improper connections can cause overheating, voltage drop, and arcing. Article 250.4 covers grounding requirements. Grounding is essential for electrical safety. It provides a low impedance path for fault current to return to the source, which helps to trip over current protection devices and prevent electrical shock. The grounding system must be properly installed and maintained. Article 300.4 discusses protection against physical damage. Wiring methods must be protected from physical damage. This includes using conduit, raceways, or other means to protect conductors from abrasion, impact, and other hazards. Article 310.15 covers ampacity of conductors. Conductors must be sized according to their ampacity, which is the maximum current they can carry continuously without exceeding their temperature rating. The ampacity of a conductor is affected by factors such as the type of insulation, the ambient temperature, and the number of conductors in a raceway. Article 406.4 covers receptacles, cord connectors, and attachment plugs, stating that receptacles installed in damp or wet locations must be listed for those locations and must be protected by ground fault circuit interrupter, or GFCI protection. Receptacles must be properly grounded and installed in accordance with the manufacturer's instructions. Article 590 covers temporary installations. Temporary electrical installations, such as those used during construction, must be installed and maintained in a safe manner. Temporary wiring must be protected from physical damage, and all equipment must be properly grounded. GFCI protection is required for receptacles used in temporary installations. When it comes to tool maintenance and safety, firstly, regularly inspect your tools for damage. Check for loose handles, cracked insulation, and worn cutting edges. Replace or repair damaged tools immediately. Secondly, clean your tools regularly to remove dirt, grease, and grime. Use a wire brush or solvent to clean metal parts and a damp cloth to clean handles. Thirdly, lubricate your tools regularly to keep them working smoothly. Use a light oil or grease to lubricate moving parts. Fourthly, store your tools in a dry place to prevent rust and corrosion. Keep them in a toolbox or tool belt to protect them from damage. Fifthly, use the right tool for the job. Don't try to force a tool to do something it wasn't designed to do. This can damage the tool and cause injury. Sixthly, wear appropriate personal protective equipment, or PPE, such as safety glasses, gloves, and a hard hat when using tools. Seventhly, keep your work area clean and organized to prevent accidents. Eighthly, never work on electrical equipment while it is energized unless you are qualified and authorized to do so. Ninthly, always de-energize and lock out/tag out equipment before working on it. Tenthly, follow all safety procedures and regulations when working with electrical equipment. To address electrical safety around the house, firstly, regularly inspect electrical cords and plugs for damage. Replace damaged cords and plugs immediately. Secondly, don't overload electrical outlets or circuits. This can cause overheating and a fire hazard. Thirdly, use ground fault circuit interrupter, or GFCI, outlets in areas where water is present, such as bathrooms, kitchens, and outdoor areas. Fourthly, keep electrical appliances away from water. Fifthly, never use electrical appliances with wet hands. Sixthly, teach children about electrical safety. Seventhly, install smoke detectors and carbon monoxide detectors in your home. Eighthly, have your electrical system inspected by a qualified electrician regularly. Ninthly, know the location of your electrical panel and how to shut off the power in an emergency. Tenthly, if you experience any electrical problems, such as flickering lights or sparking outlets, call a qualified electrician immediately. Furthermore, for selecting the right multimeter, consider firstly the type of multimeter that includes digital multimeters, or DMMs, which are the most common type, offering a clear digital display of measurements. Analog multimeters use a needle to indicate measurements on a scale, which can be useful for visualizing changes in values, but they are less precise than digital models. Clamp-on multimeters are designed to measure current without breaking the circuit, making them ideal for high current applications. Secondly, measurement ranges and accuracy are important. Ensure the multimeter can measure the ranges of voltage, current, and resistance you'll be working with. Look for a multimeter with high accuracy, typically specified as a percentage of the reading plus a number of digits. Thirdly, safety features should be considered. Choose a multimeter with appropriate safety ratings such as Cat Roman 3 or Cat Roman 4, depending on the types of circuits you'll be testing. Also, look for features like overload protection, high voltage protection, and fused inputs. Fourthly, features and functions are important. Common features include auto-ranging, which automatically selects the appropriate measurement range, continuity testing, diode testing, frequency measurement, capacitance measurement, and temperature measurement. Fifthly, display and ergonomics should be considered. Look for a multimeter with a large, easy-to-read display, preferably with a backlight for use in dimly lit areas. The multimeter should also be comfortable to hold and use, with well-placed buttons and a rugged design. To consider voltage drop calculations, firstly, understand the formula for voltage drop, which is voltage drop equals current times resistance, or volts drop equals I times R. In alternating current, or AC, circuits, you may also need to consider impedance, or Z, which includes resistance and reactance. Secondly, determine the conductor resistance. Use tables provided in the National Electrical Code, or NEC, such as Table 8 in Chapter 9, to find the resistance per foot of the conductor you're using. This value depends on the conductor material, size, and temperature. Thirdly, calculate the total conductor length, multiplying the one-way distance of the circuit by 2 to account for the return path. Fourthly, calculate the voltage drop, multiplying the current, resistance per foot, and total conductor length to find the voltage drop. Fifthly, compare the calculated voltage drop to the allowable voltage drop, which is generally 3% for branch circuits and 5% for feeders. If the calculated voltage drop exceeds these limits, you'll need to increase the conductor size or take other measures to reduce the voltage drop. For example, consider a 120 volt circuit with a 20 amp load running 100 feet using 12 American wire gauge or AUG copper wire. The resistance of 12 AWG copper wire is approximately 1.588 ohms per 1000 feet, or 0.1588 ohms per foot. The total conductor length is 200 feet. The voltage drop is 20 amps times 0.1588 ohms per foot times 200 feet, which equals 6.352 volts. The percentage voltage drop is 6.352 volts divided by 120 volts times 100%, which equals 5.29%. Since this exceeds the 3% limit for branch circuits, you would need to use a larger wire size, such as 10 AWG, to reduce the voltage drop. For conduit bending techniques, firstly, understand the basics of conduit bending, including the different types of bends, such as 90-degree bends, offsets, kicks, and saddles. Also, understand the terminology used in conduit bending, such as stub-up, gain, and take-up. Secondly, choose the right type of conduit bender, which includes hand benders for small diameter conduit, such as 1/2 inch and 3/4 inch, hydraulic benders for larger diameter conduit, and electric benders for high volume bending. Thirdly, prepare the conduit, cutting the conduit to the desired length and deburring the ends to remove sharp edges. Fourthly, make the bend, positioning the conduit in the bender and applying pressure to create the desired bend. Use a level to ensure the bend is accurate. Fifthly, check the bend, using a protractor or angle finder to verify the angle of the bend. Also, check for kinks or other imperfections in the bend. For example, to make a 90-degree bend in 1/2 inch electrical metallic tubing, or IMT, using a hand bender, firstly, measure the desired stub-up length, which is the distance from the end of the conduit to the start of the bend. Secondly, mark the conduit at the stub outlet. Thirdly, position the conduit in the bender with the mark aligned with the arrow on the bender. Fourthly, apply pressure to the bender handle, pulling the conduit through the bender until you reach a 90-degree angle. Fifthly, check the bend with a level to ensure it is accurate. When pulling wire through conduit, firstly prepare the conduit, which includes ensuring that the conduit is properly installed and supported and that all connections are tight. Also, make sure the conduit is clean and free of debris. Secondly, choose the right type of wire lubricant. Use a wire lubricant that is compatible with the type of wire and conduit you're using. Avoid using petroleum-based lubricants, as they can damage the wire insulation. Thirdly, attach the pulling rope or wire to the wires. Use a wire pulling grip or basket to securely attach the pulling rope or wire to the wires. Fourthly, feed the wires into the conduit, feeding the wires into the conduit by hand or using a wire feeding machine. Fifthly, pull the wires through the conduit, pulling the wires through the conduit using a hand or power pulling device. Use a steady, even pull to avoid damaging the wires. For example, to pull 312 AWG conductors through a 1-inch conduit, firstly, ensure the conduit is properly installed and supported. Secondly, apply wire lubricant to the wires. Thirdly, attach a wire pulling grip to the wires. Fourthly, feed the wires into the conduit. Fifthly, pull the wires through the conduit using a hand pulling device, ensuring a steady pull. When terminating wires to devices, firstly, prepare the wire, stripping the insulation from the end of the wire to expose the conductor. Use a wire stripper to avoid damaging the conductor. Secondly, choose the right type of connector. Use a connector that is suitable for the type and size of wire you're using and for the type of device you're connecting to. Thirdly, connect the wire to the device, inserting the wire into the connector and tightening the screw or clamp to secure the wire in place. Fourthly, test the connection, tugging on the wire to ensure it is securely connected. Also, check the connection with a multimeter to ensure there is good electrical continuity. Fifthly, insulate the connection, wrapping the connection with electrical tape or using a heat shrink sleeve to insulate the connection and protect it from moisture and corrosion. For example, to terminate a 12 AWG wire to a receptacle, firstly, strip the insulation from the end of the wire. Secondly, loosen the screw on the receptacle terminal. Thirdly, insert the wire into the terminal and tighten the screw. Fourthly, tug on the wire to ensure it is securely connected. Fifthly, wrap the connection with electrical tape. For troubleshooting common electrical problems, firstly, identify the problem. Determine the symptoms of the problem and gather information about when and how the problem occurs. Secondly, check the power source, ensuring that the power source is working properly and that the circuit breaker or fuse is not tripped. Thirdly, inspect the wiring, checking for loose connections, damaged wires, and other signs of problems. Fourthly, test the components using a multimeter to test the components in the circuit, such as switches, receptacles, and appliances, to determine if they are working properly. Fifthly, replace the faulty components, which include replacing any components that are found to be faulty. For example, if a light fixture is not working, firstly, check the bulb to see if it is burned out. Secondly, check the switch to see if it is working properly. Thirdly, check the wiring to see if there are any loose connections or damaged wires. Fourthly, test the light fixture with a multimeter to see if it is receiving power. Fifthly, replace the bulb, switch, or wiring as needed. Table 310.15. B16 in the NEC provides ampacity ratings for conductors based on insulation type and temperature rating. It is essential to select conductors with the correct ampacity for the intended application to prevent overheating and potential fire hazards. The table lists ampacity values for various conductor sizes and insulation types, such as THHN, THHW, and XHHW, at different temperature ratings, such as 60 degrees Celsius, 75 degrees Celsius, and 90 degrees Celsius. For example, a 12AWG copper conductor with THHN insulation rated for 75 degrees Celsius has an ampacity of 25 amps, while a 10AWG copper conductor with the same insulation and temperature rating has an ampacity of 30 amps. Derating factors may need to be applied if there are more than 3 current-carrying conductors in a raceway or cable, or if the ambient temperature is higher than 30 degrees Celsius.